Thank you very much. And it is a pleasure to me to introduce you Anna Siffert. She is going to talk about a construction of p-harmonic maps. Sorry.
So thank you very much for the invitation and for the introduction, of course. So everything I say today is joint work with Volker Branding from the University of Vienna. So as you said already, I will talk about the construction of p-harmonic maps. And the main goal is to prove the following theorem. Which appeared last year in arXiv and will be published this year in Calqua. So we proved that for P and N given, and for M and N, which satisfies the following inequality, namely P is strictly less than M, M is strictly less than P plus 2 times square root of P. There exists infinitely many p-harmonic self-maps of the sphere Sm. Okay, so that's the goal I want to prove today. And let me start by saying that here, throughout the talk, I'm talking about self-maps. This is not necessary. I could also have talked about p-harmonic maps between spheres of different dimensions, but for easiness of presentation, I restrict to self-maps. So my talk is divided into two parts. In the first part, I will introduce p-harmonic maps and will say a bit about known results. And in the second part, I will sketch the proof of this theorem. So let's start with the first part, which is the introduction. So I start by defining p-harmonic maps. A smooth map between closed Riemannian manifolds is said to be p-harmonic, where P is an M and P is assumed to be larger or equal than 2. So phi is called p-harmonic if and only if this map phi is a critical point of the following energy functional, namely of EP phi, which is defined to be 1 over P integral over M d phi to the power P times the volume form with respect to G. And I call this energy functional 1. So I said that we assume the manifolds to be closed. This is just for the easiness of presentation. Again, I can also define p-harmonic maps between non-closed Riemannian manifolds. So before I say a few words about existence and regularity, let me remark that for the special case P equals 2, one talks about harmonic maps, and harmonic maps are well known in the literature and have been studied for decades. And so-called harmonic maps include geodesics. And for example, they have a nice connection to minimal surfaces, namely isometric immersions from M to a Euclidean space RD. Such an isometric immersion is minimal if its coordinate functions phi I are harmonic. So this is a nice connection to minimal surface theory. And of course, there are a lot of applications of harmonic maps within mathematics and also in physics, for example, in elasticity theory. So I don't want to go into details here, just let me add another remark, namely this energy functional here is quite natural. So you might know this energy functional for the case where p equals 2, and you might have encountered this. And you might also know that for p equals 2 and the dimension of the domain manifold m equals 2, 1 is conformally invariant. And it's also known that if p equals 2 and m is larger than 2, then 1 is not conformally invariant. So this is both well known. And then one might, of course, ask which energy is a natural candidate to consider in higher dimensions, and the answer is 1, because 1, this energy I introduced a few minutes ago, is conformally invariant for p equals the dimension of the domain manifold, namely m, which I denoted by m. In this sense, the energy functional is a natural choice. So then let me go on. Let me go back, and I introduced p-harmonic maps to be critical points of the energy functional. And it is straightforward to verify that these critical points are characterized by the following partial differential equation, system of partial differential equations. Namely, you consider the trace of this expression here, and this should vanish. And usually the left-hand side is denoted by tau phi. So, and this is called tension field. And this equation constitutes a quasi-linear elliptic system of PDEs, quasi-linear elliptic system. And this system degenerates at points where d phi, the norm thereof, vanishes. And this implies that you cannot expect to gain regularity from elliptic theory due to this degeneration. There exist regularity results, but they are weaker compared to the case p equals 2, where you don't have these degenerate points, because in this case, this term equals 1. Okay, so I don't want to concentrate on regularity in this talk. I want to concentrate on existence. So let me begin by saying that there had been a few constructions where p-harmonic maps between specific spheres have been constructed. For example, Ishida constructed one p-harmonic map between specific spheres in 1996. And there has also been work by other authors like Kawai, Nakushi, and Takeuchi, who also constructed some p-harmonic maps between specific spheres, only finitely many. And then I want to mention that in the specific case, p equals 2, where we are back to the harmonic map case, there's a result due to Bison and Schmey from 96, and they proved that for 2 less than m less than 6, yeah, there exist infinitely many harmonic self-maps of the sphere Sn. And this result we want to generalize to the case where p equals 2. And we will do so in the following. Yeah? So let me start the second section. This is the sketch of the proof of the main theorem. Okay, so before I can sketch the proof of the main theorem, I have to provide some preliminary results. And I start by first introducing a natural parameterization of the sphere. Namely, we will consider the round sphere. We will parameterize it in the obvious way. We will introduce a parameter t, which is real, and parameter phi, which is for the sphere of one dimension less. And then we will consider equivariant maps between these spheres. And then I will provide the ODE we are considering. So we deal with the sphere endowed with the round metric. We consider the parameterization I just mentioned, namely we consider parameterization t phi, where t is between 0 and pi, and phi is in the equator sphere. And then we consider the following maps, the equivariant maps, namely we consider maps phi from SM to SM, with just map t phi to RT phi. In some sense, we are just reparameterizing this closed interval. Okay, you can think of the sphere, well, it's endowed with the action of SON. Yeah, so we are considering the rotational symmetric case. Now, it turns out that the following variable transformation will be helpful for our later considerations. Instead of considering t, we want to consider the variable x. So, in other words, here, this boundary t equals 0 is mapped to x equals minus infinity, and t equals pi is mapped to x plus infinity. It also turns out that it's useful to shift the function r. We shift it by pi over 2, and we do this for symmetry reasons. This will become apparent in a few minutes when I discuss the numerics. Okay, so this is the variable transformation, and now what we can do, we can plug this ansatz into the energy functional, so the formula for the energy functional, and calculate the corresponding Euler equation, so the critical points. And well, I prepared this already because the equation is ugly. So let me just copy this and plug it in here. So this is what we obtain when we calculate the critical points of this energy function. Now you see that this is an ordinary differential equation. And this is not, well, that's not a surprise. Yeah, so I said at the beginning, we have PDE in general, but we imposed a lot of symmetry here. Yeah, and the symmetry is such that the original PDE reduces to an ODE, and this is a very common ansatz or approach in a lot of branches in differential geometry. So we impose a lot of symmetry here. So let me say a few words about this ODE we are considering. So this is the second second order ODE in this function, for this function h. We have here this fraction a1 and this fraction a2. It will become clear later that it's very important that these fractions are bounded. They are the absolute values of this fraction is bounded by 1 in both cases. Why is this so important? Because, well, if we go back to the case p equals 2, where we are considering harmonic maps, then this ODE reduces to this ODE here. And this is basically what the ODE which has been studied by Bison and Schmey, and this is what is known in the literature. Yeah? And now if you compare these two ODEs, you see these are the additional terms which come in, and they are bounded by 1, and this gives us hope to well, this gives us hope to be able to proceed to use a modified strategy which was used by Bison and Schmey, and that's what we actually do. So first of all, it turns out that it's useful to introduce capital A, the function capital A, which is defined this way. Why? Because with the help of this function A, we can introduce a Lyapunov function. So we define W to be given by this expression here. And by a straightforward computation, you can prove that this is monotonically increasing on the positive x-axis if m is larger or equal than p. So this is a Lyapunov function. We found it by trying. Yeah? So this took us quite a lot of time to guess this Lyapunov function, and the existence of this Lyapunov function is crucial for the rest of our proof. Yeah? Proving that it's a Lyapunov function is not hard. You just take the derivative of W and plug in the Euler-Lagrange equation I provided here, and then this is straightforward. Okay, now we did a lot of numerical experiments before we started to do this proof, and we saw that all solutions to this ODE have a symmetry. They are either point symmetric with respect to the origin, or they're symmetric with respect to the y-axis. So we can't prove this. We can't prove that they actually have the symmetry, but what we will do now is we will impose one of these symmetries, and we will just construct solutions having this symmetry. So in other words, we will provide infinitely many solutions having these symmetries, but we can't prove that these are actually all solutions which exist to this ODE. So we assume the following, namely we assume that the initial value of h at 0 is 0, and the initial velocity of h at 0 is b. And a solution of the Euler-Lagrange equation with this initial values is called hxb, yeah? And we call it b orbit. And now, in other words, we are considering solutions which are point symmetric with respect to the origin, so they are odd. And you can proceed along the same lines for even solutions. I restrict myself to odd solutions in the rest of this talk. So the first observation we have is that we have good control over the W1, 2 norm of H. In other words, H stays close to the x-axis provided that the initial velocity b is small enough. So this is the contents of lemma 1. So let me just state this, what I said. So H stays close to the x-axis provided the initial velocity b is small enough. And formally this says, given any x0 larger than 0 and any beta larger than 0, there exists an epsilon depending on this x0 and beta, positive of course, such that if the initial velocity b is less than epsilon, then this W1, 2 norm of H, namely this expression here, is less than beta for x being less or equal than 0, and of course positive. Yeah. So okay, so how to prove this result? This is not very hard again. We use mainly we use this Euler-Lagrange equation. Let's call it 2. So we use 2 and the fact that these functions AI are bounded, the absolute value of these functions AI is bounded by 1, to show that the derivative of O squared is bounded from above by some constant, positive constant c times O squared x. But this immediately implies that this rho is bounded by e to the power cx times rho 0. So in other words, if the initial velocity b, which is rho 0, by assumption, is less than e to the power minus c x0 times beta, then rho x is less than beta for all x less than x0. So this is more or less elementary. You just have to, you just have to use the Euler-Lagrange equation and this fact to get this estimate here. This is, that's not hard, but you have to write a few lines here, but this is the essential ingredient. Now we have the following results. I proved the existence of the Lyapunov function, and we have this good control over the W1, 2 norm of H. And let me say a few words about the numerics. So I prepared this already. The numerics suggest the following. So we always start with H0, and then consider this blue solution. Here the initial velocity b is rather large, and this blue solution leaves the stripe minus pi over 2 at some point and never comes back. Then we decrease the initial velocity a bit and have this red solution. This red solution also leaves the stripe and never goes back. Then if we even decrease the initial velocity more, we will eventually have something like this green solution, where this first increases a bit, then leaves the stripe at minus pi over 2 and then goes off to minus infinity. And the hope is, of course, to find the purple solution in approaches this pi over 2 as x goes to infinity. And that's, and we will prove, of course, as the initial velocity decreases, we get solutions with an increasing number of zeros. And we will distinguish the solutions we construct, these infinite solutions we construct by their number of zeros. And for this purpose, it's helpful to introduce the rotation number. This rotation number basically counts the number of zeros. For this purpose, define theta by theta 0b to be pi over 2, and theta xb to be given by this expression for x larger than 0. So it's the reason why it's called rotation number is that, of course, in phase space, that's the rotation number. So the rotation number is then defined to be theta b is the scaling factor times theta at xeb, where I still have to introduce this xe. Well, and this xeb is the smallest x larger than 0, for which the b orbit exits the stripe. The stripe gamma, which I introduced here. So the stripe gamma is just this area, and we can prove that as soon as a solution exits the stripes, it never comes back. So if it exits the stripe at pi over 2, it goes off to infinity, and if it exits the stripe at minus pi over 2, it goes off to minus infinity. Okay, so this is the rotation number, and now I want to provide a third preliminary result, namely lemma 2. And this lemma 2 states that the first derivative of theta is uniformly bounded. So again, let x0 larger than 0 be given, and assume that rho is close to 0, which you can do by lemma 1, and assume again that we have this inequality which I stated at the beginning, namely this inequality here. Okay, so then the first derivative of theta is uniformly bounded from above by some negative constant CMP. CMP is positive, but minus CMP is negative, for x in 0, x0, where CMP is positive. Okay, so this is not a straightforward. This is an elementary calculation I don't want to provide. You just have to take the first derivative of theta. You have to plug in the Euler-Lagrange equation. You have to rearrange in the right way, and you will finally get this result. This is, all the calculations are elementary. The key step is to separate the terms in the right way. So I don't want to provide this calculation because it's rather awful. I want to conclude something from it. So I want to conclude that the rotation number is arbitrarily large. So that's the heuristics. The right formulation is the following. Let me give this a number. So assume that this inequality 3 is satisfied again. Then for n larger than 0, there exists an epsilon, of course, larger than 0, such that if the initial velocity b is less than epsilon, then the rotation number is larger than n. So this is what I mean by the rotation number becomes arbitrarily large. So the heuristics is if you have a small initial velocity, then the rotation number or the number of zeros of the solutions to the Euler-Lagrange equation will be rather large. So the proof is now elementary with the preparation at hand. So let x0 be n times pi divided by CMP, the CMP which appeared in the previous lemma. Then theta x0b minus theta 0b can of course be written as this integral over the first derivative of theta. And this is less than minus n. And since by assumption rho is very small for x less or equals than x0, we have that the exit point xeb is larger than x0. Yeah. So because if rho is very small, the solution is close to the x-axis, meaning that at this point the solution cannot have exited the stripe. Yeah? So this means that the exit point lies after x0. And this implies that the rotation number is larger than x minus 1 over pi times theta at x0, missing the b, sorry for this, minus theta at 0b. And this is, of course, larger than n by this inequality here. And this provides the proof. Yeah? So the main ingredient here is this boundedness of the first derivative of theta, which I provided in lemma 2. Okay, so we are almost done with the preparation. The last preparation I want to give is the following. Namely, if I have a solution of the Euler-Lagrange equation which stays in the stripe for all x larger than 0, and if h has finitely many zeros, finite number of zeros, then the limit of hxb as x goes to infinity is plus or minus pi over 2. Okay, so why is this important? I suppressed this discussion so far. Let me go back to the Euler-Lagrange equation. I said somehow sloppy, we want to construct solutions to this ODE here. Yeah? And of course, we have to have solutions with the right boundary values. And the right boundary values to have solutions which are actually smooth turn out to be pi over 2. Yeah? So in this sense, this is actually what we want. And to prove this lemma 3, that's not hard. If you assume that you just have finitely many solutions of finitely many zeros, and that this h stays in the stripe for all times larger than 0, then you just plug into the Euler-Lagrange equation and you get this immediately. Yeah, that's not hard. You actually have to solve the initial value problem at minus infinity or plus infinity to provide regularity, to provide smoothness. But I don't want to give the details here. I just want to say, well, that's possible. Okay, with this preparation at hand, I can now sketch the proof of the theorem. So I will combine the results we had so far. Remember that the heuristics is if the initial velocity b is small, then the number of zeros of the solution is rather large. So I will now construct a solution which has exactly 1 0, and then I will do the induction step. So the proof is by induction, and we will first construct the first orbit, then I will do the induction step, and then we are done. So let's construct the first orbit. For this purpose, set S1 to be the set of B's for which the B orbit exits the stripe gamma via pi over 2 with rotation number of B being less or equal than 1. So the picture is this one. So we are talking about orbits which satisfy this, which have this qualitative behavior. So why is S1 non-empty? Well, it's not empty due to the following. Remember, I introduced this Lyapunov function W, and the W at 0, if I just plug in, is given this way. This in particular implies that W0 at 0 is, so W at 0 is larger than 0 for initial velocity large enough. But since we know that W is monotonically increasing, this implies that Wx is larger than 0 for x being greater or equal than 0. Now, using the specific form of W, we get that h, the first derivative of h, is positive for all x larger than 0. But this implies that S1 is non-empty. Yeah? This implies the existence of such a solution, which I draw here. Okay, now remember in the heuristics, it's quite natural that we want to consider the infimum of S1. Yeah? So we hope that, well, at some point we will have a solution like this one. Yeah? So that's why we're considering the infimum. The proposition 1 guarantees that B1 is larger than 0. Remember that if the initial velocity becomes very small, the number of zeros increases. Yeah? So this guarantees that B1 is actually 0. And we also know that the B1 orbit cannot exit the stripe gamma via pi over 2, because the same would hold true for nearby orbits with B less than B1. And that's a contradiction to the definition of B1. So this means that the B1 orbit stays in gamma for all times larger than 0. And now lemma 3 implies that the rotation number is actually 1. Okay, so this is the first step. This B1 orbit provides the first orbit, and now we do the induction step, and that's the main step. Okay, so for this purpose, let me introduce S2 to be the set of B for which the B orbit exits gamma via minus pi over 2, and the rotation number is less or equal than 2. So we would like to do the same as before. So we would like to prove that S2 is non-empty, and then we consider the infimum of S2 and thus construct a second orbit with initial velocity B2. So the only thing which remains to prove is that S2 is non-empty, and that's the main work here. Yeah? So if we have proven that S2 is non-empty, then proceed as before, and then we are done by induction. So in the last 5 minutes, let me just explain how we prove that S2 is non-empty. First, observe that if B is less than B1, then the rotation number is larger than 1. That's by the definition of B1, which I provided above. So that's clear, that's elementary. But the other observation, that's the crucial one, namely that if B is less than B1, but close to B1, then the rotation number is less or equal than 2. Yeah? And hence S2, hence B is in S2, and this means that S2 is non-empty. Yeah? So this means if B is close to B1, but less than B1, but close enough, then the rotation number doesn't become too large, meaning that S2 is non-empty. And the idea is as follows. So remember that we have our B1 orbit here. And if we decrease the initial velocity a bit, we will have a picture like this. That's what we hope for. And assume that we have a picture like this, then there exists an XA such that the first, so that there's a critical point of H, and there exists a XB such that H at XB equals 0. So the existence of this XA and XB followed by the definition of B1. And the further thing we observe is that if B is close to B1, then XA, this XA, becomes as large as we want. So that's the further, the other observation. Now, the Euler-Lagrange equation implies that the first derivative of H is less than 0 for all X in this interval XA, XB, just as I draw it here. So it's decreasing in this interval. That's an immediate consequence of the Euler-Lagrange equation. What is hard to prove is that it's also decreasing here in this interval XB infinity. And the observation is that we have that W XB is larger or equal than 0 for XA large enough, which we can achieve since if B is close to B1, XA is as large as we want. And this here, this is the crucial step, proving that W XB is greater or equal than 0 for XA large enough. For this purpose, we have to estimate W X minus W XB in 2 ways, using the previous lemmas, and combine the 2 estimates to actually obtain this result. So this is the hard apart. Yeah? And here it crucially played provided that this inequality holds, then the monotonicity of W and this inequality 4 imply that H is decreasing for all x larger than xa, and this implies that S2 is non-empty, providing the induction step. Okay, so let me just say a few words. I said that this is the hard step. Yeah, I didn't do the estimates because of time reasons. And as I said, for this task is, can we also do a similar construction for other symmetries here? Yeah, so I considered the rotational symmetric case here. And for example, you might ask, can we do this in the birotational case? And the answer is, well, at the moment we can't, because we couldn't find a Lyapunov function for other symmetries. So that's one natural question. Another natural question you might ask is, well, for the case where p equals 2, there is a theory developed how to construct harmonic maps between compact cohomogeneity 1 manifolds. And the natural question would be, can you extend this to p-harmonic maps between cohomogeneity 1 manifolds? And the answer is, well, we can do the reduction step, namely we can provide. The problem is providing solutions to this ODE, and in general we can't. Yeah, so this rotational symmetric case is really the only case we could attack so far. Okay, so I want to stop here.
Thank you, Anna. Thank you for your wonderful talk. Are there any questions quick questions in internet audience and also in presence audience? If not, I have
a question. I do have a question. This is Christina Sermani. Can you explain a little bit more? You said that you would, there's an induction step that you would do if it's, once you show it's not empty, you proceed as before for your induction step, but I don't quite see that.
So if S2 is non-empty, yeah, then I consider B2 to be the infimum of S2, which is strictly less than B1. Yeah. So, and then so let me do the heuristics. Yeah, for B1 that's the B1 orbit. Yeah. And the other orbit looks something like this. Yeah, I can't draw it.
Right. Something like that. Yeah.
Yeah. So that's the B2 orbit. And so as I said, so again, we can prove that B2 is larger than 0, because otherwise the number of zeros would be too large. Yeah. Again, the B2 orbit stays in the stripe gamma, because again, if it would exit gamma, then this would hold true for nearby orbits with b less than b1. This would give a contradiction. Yeah, okay, here it's very heuristic. Yeah, so there.
Right,
I
that's
have to
okay.
work a bit,
Heuristic is okay.
yeah, and then again, as soon as it stays in the stripe, yeah, then this lemma 1 provides that well, the limit is either pi over 2 or minus pi over 2. Here it's because it just has 1 0, yeah, and we start here, it has to be minus pi over 2. That's how we proceed. So, but of course, yeah, that's well, it's very heuristic. We have to work a bit there.
Right. But the induction, is it going to be flipping back and forth between pi over 2 and minus pi over 2? I don't.
So that's
then what would B3 do, and then what would B4 do?
That's what we see in So we get really solutions with for each. So we can't prove. Oops, sorry. So we can't prove that we have exactly one solution with let's say 1 0 here. Yeah. So there might be many solutions with exactly 1 0, but what we see is that it's really flipping forth and back, yeah, from the numerics. So we can't exclude that we actually have more construction than what I'm claiming, more solutions than I'm claiming, yeah. But well,
no, that's all right. I just wanted a sense. So it is a sort of a flipping kind of induction.
Yes,
okay, thank
yes,
you.
Yes, that's it.
Thank you so much.
You're welcome.
Well, we have no time for more questions, so we thank the speaker again. Thank you.
Thank you.